Okay, in section 7.4, we talked about rectangles as we're getting into more specific types of quadrilaterals here. Now in 7.5, we move on into two new shapes here, rhombi and squares. So if you're not familiar with the word, rhombi is the plural of the word rhombus. So we start with that definition here, and a rhombus is defined as a parallelogram with four congruent sides. Now, just like with a rectangle here, this definition begins with the fact that a rhombus is a parallelogram. So that already tells us five important things. That its opposite sides are parallel, opposite sides are also congruent, opposite angles are congruent, consecutive angles are supplementary, and the diagonals bisect each other. But what's new in a rhombus now is the fact that all four sides here are going to be the exact same length. So somebody once described a rhombus to me as a slanty square, and I think that kind of makes some sense here. Okay, so this is what we have right here for our picture of a rhombus, and then I drew another one here over on the right, and it always bothered me a little bit because when little kids are learning shapes, once in a while, you'll see a rhombus kind of oriented maybe this way, like straight horizontally, or maybe pointing straight up and down like this vertically, and a lot of times in preschool or kindergarten, they'll tell a little kid or they'll have them learn that that shape is called a diamond. That always bothered me a little bit. In geometry, we call that a rhombus. Any four-sided figure with four congruent sides is automatically a rhombus. So this is just two examples of what they look like. Now, that's the definition of it, but there's a couple of cool things that happen here anytime you have a quadrilateral with four congruent sides. So the first thing I wanted to do here before I just gave you guys the two theorems that are coming next right here is to ask you, what do we notice about the diagonals of our rhombus if I draw them in there? You'll notice I was really careful here, guys. I made these diagrams on GeoGebra. I didn't just freehand them because I wanted you guys to see perfectly what happens. So what I'd love for you to do is think for just a second right now, and I'm hoping you could come up with two key observations about the diagonals of this rhombus that don't necessarily happen in any other parallelogram. Well, one of the things I'm hoping you'd notice here is that it certainly looks like this is a 90-degree angle right here where the two diagonals intersect. And that is, in fact, the case. We're going to get to that as a theorem in just a second, but I want to talk about why that is. It's not just an assumption at this point right here. Because a rhombus is also a parallelogram, we know that the diagonals bisect each other. That means that this piece right here and this piece right here have to be congruent to each other. And likewise, that long diagonal gets split in half as well. So I'll put a triple tick mark here and a triple tick mark here. Now, what I just drew in red happens in any parallelogram, but because this is a rhombus, all four of these sides here, the original four sides of the quadrilateral, are congruent as well. And what that means here, if we look at it carefully, is that the diagonals that we drew cut our rhombus into 1, 2, 3, 4 triangles here, all of which, take a look, have a side with 1 tick mark, they all have a side with 2 tick marks, and they all have a side with 3 tick marks. Every one of those triangles has those same tick marks right there. And what that means, I want to go ahead and jot this down right here, is that all 4 triangles that we have right here, they are all going to be congruent by, and let's go all the way back to chapter 4 here, guys. Side, side, side congruence here. When two triangles have 3 pairs of congruent sides, the triangles themselves are identical, or they are congruent. Now, what that means, everybody, is that these 4 angles here, and I guess just to not confuse everybody with the 1, 2, 3, 4, I'll call them angles 5, 6, 7, and 8. All 4 of those angles right there have to be congruent to each other. And furthermore, all 4 of those angles make a complete circle. They have to add up to 360 degrees. So if those 4 angles in the middle all add up to 360 and they're all congruent, we could just divide them by 4 and realize that each one of those angles in the center here is a 90-degree angle. So let me get rid of a lot of this junk right here and say, okay, that's a right angle, but that of course means this is a right angle, and that's a right angle, and that's a right angle. So unique among parallelograms right here, when we are in a rhombus, our diagonals are going to be perpendicular to each other. Now, another thing going along with that is because all of these triangles are congruent, this angle right here and this angle that's adjacent to it have to be congruent to each other. And the same thing would happen with this angle right here and then this angle right here next to it. And in fact, the same thing happens here, and the same thing happens here. So these are two unique things that happen in a rhombus that don't happen in a regular, I should say a normal parallelogram, one that's not a rhombus. So let's get these two theorems written down, everybody. Theorem 715 says the following: if a parallelogram is a rhombus, then its diagonals are perpendicular. So if you have this diagram in your notes, we're going to go ahead and draw 4 corner marks there to show that all 4 of those angles in the center of that figure are going to be right angles right there. So that's what Theorem 715 says. And Theorem 716 says if your parallelogram is a rhombus, this is a little wordy, then each diagonal bisects, there's a word, cuts exactly in half a pair of opposite angles. So that tells us here that this angle and this angle are congruent. And remember now, because it's a parallelogram, opposite angles were congruent. That means that this angle gets bisected as well, and I can use just one tick mark on all 4 of those angles there. But then as I get into the more narrow angle, this one gets bisected. That'll need to be a double tick mark, and the same thing is going to happen right up here with a double tick mark as well. So both of those theorems are based on the idea that we explored right here, the fact that when you draw the 2 diagonals in a rhombus, you create these 4 congruent triangles by side, 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 and that means that all the corresponding parts of those congruent triangles have to be congruent as well. That's an idea from chapter 4 called CPCTC. So maybe you remember that and maybe you don't. Okay, so now you are armed with, everybody, the definition of a rhombus here, and then 2 theorems, 2 properties that go along with that say a little bit more than just the definition itself. So let's try to knock out 2 problems right here. We're going to find the measures of each numbered angle in this figure right here. Now you'll notice the text doesn't tell you anything else about this figure, but you will notice, I hope guys, that you have got a single tick mark here and here and here and here. And even though the definition of a rhombus says that your figure is a parallelogram, that's true, it actually would have been accurate just to say a quadrilateral with 4 congruent sides. So let me say that loud and clear. Any quadrilateral with 4 congruent sides is automatically a rhombus, which makes it a parallelogram as well. So because this figure here has 4 congruent sides, we know that it's a parallelogram. Okay, and we're going to try to come up with the measures of angles 1, 2, 3, and 4. So let's start with angle 1, and what I want you to notice is where angle 1 is located, right in the middle of this figure where the 2 diagonals intersect. So we would probably want to focus right here on Theorem 715, which says that in a rhombus, your diagonals are all perpendicular. So I can put a right angle anywhere there I want, and that means that angle 1 has to be 90 degrees right on the nose. Okay, what's coming next? Angle 2. Well, to get to angle 2, we're going to go back now and focus on this theorem right here. When your parallelogram is a rhombus, each diagonal bisects a pair of opposite angles. Now let's see here, guys. The one angle that we knew was this 58-degree angle right here. So I'm kind of talking about this angle right here, and I want you guys to notice these 2 angles have to be congruent, and these 2 angles in the opposite corner, all 4 of those need to be congruent to each other. So if I had a 58-degree angle here, that tells me that this would have to be a 58-degree angle as well, and so would these 2 angles in the opposite corner right there. Because opposite angles in any parallelogram are going to be congruent, but because this is a rhombus, these 2 angles right here have to be congruent as well, because the diagonals bisect the angles that they are drawn to. Okay, so angle 2 would need to be 58 degrees, and so would angle 3, 58 also. Now, I didn't write it in the diagram, but I probably should have. Angle 1 was 90 degrees right there, and so when I ask you to come up with the measure of angle 4, there's a couple of ways of going about it, but I think that probably the easiest way is to realize here, and this has happened a lot in this chapter, that the 2 diagonals of your quadrilateral, when you drew them, intersect, and created a triangle here. I'm going to go ahead and color that thing in blue highlighter here. And anytime you have a triangle in geometry, if you know the measures of two angles, you can always find the measure of the third. So in my calculator, I would just go ahead, in fact, I'll do this with you here, take 180 and subtract the two angles that you know, 90 and 58. So 180 degrees minus a 90-degree angle and minus the 58-degree angle is going to get us the measure of the third angle, which is 32 degrees. So that means we've got a 32-degree angle right here for the measure of angle 4. Now that's as much as I asked you for, but remember guys, if these two angles were congruent, that means that 32 and this angle right here would have to be congruent, and so would the two across the figure, 32 and 32. So what I want you to notice here, guys, is a couple of things. Basically, then, all four triangles that were created by drawing the two diagonals have the same three angle measures. Each one of them has a 90-degree angle, a 58-degree angle, and a 32-degree angle. A couple other fun things. If I were to add up the 32 and the 32 here, I'd get a 64-degree angle right there. If I were to add up the 58 and the 58 up here, that gets me, if I'm not mistaken, 116 degrees. And if I were to add 116 plus 64, that's a 10, carry the 1, 1 plus 1 plus 6 is 8, and bring the 1 down, I get 180 degrees for the sum of these two consecutive angles. That shouldn't surprise you, because a rhombus is a parallelogram, and any two consecutive angles in a parallelogram need to be supplementary. They have to add up to 180, and they do. So there's a lot of ways to go about verifying your answers right here, guys, but that's the way I would handle problem C. Okay, and problem D, I don't really know if this one is easier or harder than the last one, but same setup right now. We're being asked to find the measure of each numbered angle within this figure, and what kind of figure is it? Again, if you look at the tick marks, double tick mark here, 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 and here, four congruent sides automatically guarantees that this quadrilateral is a rhombus, which also makes it a parallelogram. So, let's get working on this one right here. Now, you'll notice in this diagram, unlike in the last one, I only drew in one of the diagonals and not two. So, how are we going to go about finding the measure of angle 1? Well, what I was really hoping you guys would notice here is that when you draw one diagonal here, you form two triangles out of the entire figure. But because of the tick marks, this triangle, there we go, that I have right here that I'm putting in blue now, is a triangle with two congruent sides, and that makes it isosceles. That tells us something really we already knew, that angle 1 and angle 5 have to be congruent to each other because those two angles are opposite or across from two congruent sides. So let's go all the way back to chapter 4 when we studied triangles right here. How would we find the measures of the two base angles in an isosceles triangle? Well, we know that the sum of all three angles needs to be 180. So I would subtract my vertex angle of 130 and get 50 degrees. Now that means that angle 1 and angle 5 together add up to 50 degrees. And since they're congruent, all we'd have to do is take 50, cut it in half, and get 25 degrees now for the measure of angle 1. Gotcha. And that would also need to be the measure of angle 5 right there, 25 degrees as well. Okay, from there, how are we going to come up with the measure of angle 2? Well, once more, if we go back to theorem 716, in a rhombus, the diagonals bisect opposite angles then. So if you've got a 25-degree angle here for angle 1, angle 2 is going to need to be the exact same measure as angle 1, so angle 2 is going to need to be 25 degrees as well. And the same argument applies to angle 4 right there. That's going to have to be 25 degrees also. Okay, so how are we going to figure out the measure of angle 3? Couple of different ways to do it, but I think the easiest one is to remember that a rhombus is also a parallelogram, and in any parallelogram, your opposite angles always have to be congruent to each other. So if this angle up here is 130 degrees, this angle in the bottom left corner would need to be 130 degrees as well for the measure of angle 3. Now, lots of ways you could verify that answer, but one I want to focus on is the idea that this angle here would be 25 plus 25, so we've got a 50-degree angle here, and what do you notice about 50 and 130? The sum of those two consecutive angles has to be 180, and it is. And the same thing applies if I look at this 50 and this 130 right here, they add up to 180 also. So there's lots of different ways of verifying your answers right here, but yeah, hopefully you're feeling pretty good about that. All right, guys, that's as much as I was going to have you do with a rhombus. We were now going to move on to the second figure in this section right here in 7.5, and that's a square. And kind of ironically, out of all the figures that we've talked about here in Chapter 7 with quadrilaterals, a square is the one that you guys learned first when you were little kids. It was on one of your tests that you took going into preschool and kindergarten, but it's the last one that we talk about here in geometry because it's the most specific out of all the ones that we've talked about thus far. So there's actually two different definitions for a square. Both of them are true and both of them are right. A square is either a rhombus with 4 right angles. Now remember, by saying that it's a rhombus, that already tells us that this figure has 4 congruent sides. So a square would have 4 congruent sides and 4 right angles. But it is just as true to say that a square is a rectangle with 4 congruent sides. And by saying it's a rectangle, that means we know that this figure already has 4 right angles. So you'll notice either way you look at it, guys, a square has to have both of those qualities right there. A square has to have 4 congruent sides. So by putting tick marks here, that makes it a rhombus, but it also needs to have 4 right angles. All of these would need to be 90 degrees. Okay, so that, of course, is the basic understanding you guys need to have of a square right there. All 4 sides are congruent, and all 4 angles are congruent, meaning that they are right angles. So a square is both a rhombus and a rectangle. Oh, and because it's both a rhombus and a rectangle, that means that it is also a parallelogram. Opposite sides are parallel, opposite sides are congruent, opposite angles have to be congruent to each other. Consecutive angles, like those two, would have to be supplementary, and surely 90 and 90 add up to 180, so we're good right there. And this gets messy. I don't know if you want to do this in your notes or not, but the diagonals would need to bisect each other. Okay, like that. Now, because a square is also a rectangle, the diagonals are congruent, so I can put a double tick mark on all 4 of those little half diagonals right there. So there's symmetry all over the place in a square right here. And that actually makes square problems relatively easy to solve. So I only have one example for you guys here. Okay, I drew a square, and again, I did it on GeoGebra because I wanted this to look nice. And I gave you 2 side lengths here. One side length in the square is 8. And then this little half diagonal is a weird irrational number here, guys, called 4 times the square root of 2, or just 4 root 2. Now, depending on whether or not you've done your trigonometry chapter yet, and for us, as I'm recording this right now, we have not done chapter 6 in this book on trigonometry, you might not know where that 4 root 2 comes from, but if you have done trig already, you're going to know that wasn't just a random number that I made up. And I would be lying to you guys if I gave you a nice number here like 5, because there's no way that that piece right there can be 5 if your side length is 8. I'll spare you all the trigonometry to figure that out, but this is what you got. And my directions were very vague here. Find every side length and angle measure in the following square. Okay, well, let's deal with side lengths first here, guys. So a nice thing about a square here is that all 4 sides are congruent because a square is a rhombus. So if my top side is 8, that means my bottom side would need to be 8 as well, and so would the left side, and so would the right side. Then, because a square is both a rhombus and a rectangle, and a parallelogram for that matter, all 4 of the little half diagonals would have to be congruent as well. So if this piece right here had a length of 4 root 2, so would this piece here, 4 root 2. And because we're dealing with a square, which is also a rectangle, these 2 pieces here would both need to be 4 root 2 as well. So that's it then, guys. We now have the length of what? All four sides and all four half diagonals. So now let's start talking about angle measures. And you'll notice here, guys, no angle measures were given to you in this figure at all. But because we were told we're dealing with a square, we already know a lot. For starters, all four big angles in this figure would need to be 90-degree angles. And the diagonals that are drawn here, because a square is a rhombus, are going to bisect those 90-degree angles. So what's half of 90? This would be a 45-degree angle here, and so would the one right next to it. Let's jump all the way across the figure right now. Opposite angles would have to be congruent, and it's a square, so I know that angle is 90 as well. But once more, the diagonal bisects that 90-degree angle, and we get some 45s. Well, that should sound familiar because the exact same thing happens in the bottom left corner and in the upper right corner. Those were both 90-degree angles, but because a square is a rhombus, the diagonal bisects those 90-degree angles, and we get 45 and 45 here, and 45 and 45 here. Now, last thing I want to talk about are the four angles in the middle of this figure. Okay, now you could probably guess just by looking at it, but remember, guys, a square is a rhombus. It says right there, and in every rhombus, where did I go? Let's take a look at Theorem 715. In every rhombus, which includes squares, the diagonals are perpendicular to each other. So that tells us, without guessing here, guys, that all of these angles in the middle have to be 90-degree angles as well. So yeah, they definitely look like 90-degree angles, but that theorem kind of verifies that for us. So I think, everybody, that's as much as I could ask you to do in that problem right there. Now, I do want to point one thing out. If the side length hadn't been given to you here or here, we wouldn't know this, we wouldn't know this, or that, or that, or that. If this was a much larger or much smaller square, those side lengths would all be different. But what wouldn't change are the angle measures. So all of these 2, 4, 6, 8, 10, 12 angles that we have right there, guys, the 45s and the 90s, that's going to be true for any square that you have, no matter how big or how small that square is. So the size of the square is not going to impact the angle measures. It is, of course, going to impact the lengths of the sides, so I'll put all those back in there, but that's where we're at for that. Now, the last thing I have for you guys in this section here is a list of theorems that's a little bit long. Sorry, I wouldn't really recommend that you guys write all these down in your notes, but I just want you guys to be aware that all of these theorems, there are 5 of them right here, they do exist, and these are things we're going to use at the end of this chapter when we talk about ways of testing for special quadrilaterals. So Theorem 714, I really should have put that in the previous section, but to be honest, I forgot to do it, so I'm going to cram it in there right now, but in the future you might already have this theorem in your notes from 7.4, tells us that if the diagonals of a parallelogram are congruent, then you know you're dealing with a rectangle. So if you already know that your figure is a parallelogram, you should test the diagonals. And if the diagonals end up congruent, then you are dealing with a rectangle. Now the 4 theorems that belong here in 7.5. Theorem 717 says that if you know you have a parallelogram, and if you test the diagonals and find out that they are perpendicular, then your parallelogram would have to be a rhombus. Okay, so that's Theorem 717. 718, now, if one diagonal of a parallelogram bisects a pair of opposite angles, then you know that your parallelogram you're dealing with must be a rhombus. Theorem 719, again, if you're dealing with a parallelogram and if 2 consecutive sides of the parallelogram are congruent, then you know your parallelogram must be a rhombus. Most parallelograms kind of work like this, guys, where the left and right have to be congruent, the top and the bottom have to be congruent, but usually they're not all congruent to each other. But this theorem is saying that if you ever have a parallelogram that looks like this and 2 consecutive sides are congruent, well, let's think about that. Opposite sides in a parallelogram always have to be congruent to each other. So if the top gets 1 tick mark, so does the bottom. If the left gets 1 tick mark, so does the right. Oh, And that means that all four sides then would end up being congruent, and that makes that a rhombus. And the last theorem here, 720, says that if you are dealing with a quadrilateral and it's both a rectangle and a rhombus, a rectangle tells you it has 4 right angles, a rhombus tells you that it has 4 congruent sides, then you know that the quadrilateral you're dealing with must be a square. So again, if I were you guys, I would just maybe take a picture of this slide, have those theorems handy. If I ask you to use those on a quiz or a test, which I very well might do, I would give you those theorems typed out on that quiz or test so that you have them there to reference and just ask you which one would apply to a diagram that you've been given. So I wasn't really going to give you any problems with those theorems right there, but those might come in handy in the future. All right, guys, that's everything I have for you here on Section 5 on rhombi and squares. So let's give that homework a try and let's see how you do.